Okay, guys, good morning. No, so our class again no, is being recorded right now. No, may I request Claire, no, Panes, to open us with a word of prayer.
Let us pray. Lord, thank you for this day. Thank you for all the blessings you have given to us. We pray that you will guide us throughout this discussion and protect us from any harm. Please give us the presence of mind to listen to our teacher, and please guide our teacher to teach us today. In Jesus' name we pray. Amen.
Amen. Now, thank you, Claire, for opening us with a word of prayer. Now, let me just run through. No, I checked already partly the attendance. No, while you were getting in earlier. Now, let me just call. No, if Bricks Jacinto is there. Bricks, not there. Maven Miranda. We have Nel, no? Nel Monteclaro, and John Nicole Rubio. No? Are you there? Now, if in case you are there, kindly tell me that you have entered the class. No, I think Mark Tamagos is not also with us. No, so later now when these students get in, we will just check their names. Now, guys, I've been talking about the importance of your completion of your performance tasks. And again, I want you to do that make-up activity. So once it is ready, once the submission button is ready, so try to make it ahead of time. So you will just simply upload the makeup activity. Again, the makeup work, for those who have valid reasons that they missed it, now we'll have an opportunity to cover up that 45% requirement of the grade. So I don't want you to miss that because that's a very heavy part of your component of your grade. Now for this morning, we will have, or for today, we will have this lecture on electric resistance. This is a review lecture. And last time when we talk about this one, so let's now go to the actual discussion. So we learn about current, and current is the rate of flow of the charge, and we label it as Q over T. And with these equations, now Q over T, we relate it with electric potential, if you recall that, and eventually come up with some energy equations and an equation on electric power or electrical power. We will see those equations again as we move along. So this is our current. And we also discussed last time about Ohm's law. So we related that one, Ohm's law, we related the concept of resistance, the idea of a current, and the potential, or potential difference in this case. So another word for potential difference, we call it as voltage. So a voltage is a kind of idea, like a force. That's the one that pushes the current to travel in the wiring. Now, the three variables, voltage, current, and resistance, are labeled as V, I, and R, and we put it in an equation called the Ohm's law. So our concept again of Ohm's law, when we divide together, when we divide the variables V by I, that principle is telling us that it gives us a certain constant R, which we call as resistance. So that resistance is also something that we see in our wiring. So our wire happens to contain as well resistance. Now, so in terms of the wiring, and the resistance in the wire, this is how we relate our resistance there. It is somehow related to the length of the wire. So if you have a wire as big as this one, so let's just draw a representation of a wire. Maybe let's just use a black color here. So maybe this is our wire again, and it has length, of course. So some wires are shorter. We have wires also that are designed, no, really, really long, no. So it depends on its use. So these two factors, length and the cross section, no? So our cross section again is this circular portion in front, no? How big is that area? We call it as again a cross-sectional area, no? And we solve the cross-sectional area in terms of a circle. So the equation of the circle is needed there, no, to solve it. Now we kind of relate it now to R, no. So A and R are inversely related, while length and R, no, or resistance are directly, no, proportional, no. Now there's a factor here that affects also our resistance, which we call as resistivity, no? And we will see a list of values for our resistivity because we realize that it is a property of a certain metal, no? There's a numeric value to this resistivity value, no? Now what I'm talking about resistivity is this symbol that looks like letter P, no? But we call this as rho, no? The letter rho in our Greek letters, no. Now our our resistivity again, no, comes in sets of values. And what are these values again, no? So let's just have, no, the next slide. So here is probably, no, a picture of our resistivity values. So these resistivity values, no, they have there are those that have the lowest resistivity values, and there are those the materials, no, that have the greatest or highest value, no. Now among those with the lowest value are the best conductors. Now we describe them to be the best conductors if they have the least resistivity value. Now the unit of the resistivity here is in ohm meter. And from here, no, copper, silver, gold, aluminum are among the best, no? And maybe, no, top of the list will be silver because, no, its resistivity value is 1.59, no? Now they have the an exponent here, no? They have 10 to the minus 8 value, and we can simply compare this number, no, the first three digits in front. That again, from these lists, the lowest will be silver, but comparing that to silicon, no? Silicon is very big, no? 640, no? Nichrome is also very big, no? In terms of 10 to the minus 8 value. It's 150, no? Now I'm pointing out nichrome because we will mention it, no, in an example later. So again, no, nichrome being or having, no, one of the highest resistivity is a very, very resistant, no, in terms of charges. This material is resisting the flow of charge, no. So therefore, no, it is having a very high resistivity, and it will heat up, no, whenever you use nichrome, no? Now again, no, how we apply resistivity is that those with the low, no, very low resistivity are considered very good, no, good electric conductors. And good insulators are those with very high, no, resistivity. So among them, rubber, no? Look at rubber, no? It's 10 to the 13. And I think, no, in most safety shoes, no, of electricians, those that go up, no, the ladder, no, in some electric poles, they wear these safety shoes that have very good, no, rubber, no, rubber sole, no. The rubber sole there, no, prevents them from being electrocuted because, no, they are kept, no, at a safe distance from the ground, no. The ground is where the charge always goes, no, whenever there's a fault there, no. So it keeps, no, the electrician safe when they wear this standard, no, rubber shoes. So again, no, rubber is one of the materials with very high resistivity, no, because it's a very good insulator, no? So again, I'm talking about resistivity, no? Now resistivity again is also affected by temperature. So they are listed now with a specific temperature of 20 degrees Celsius because perhaps now at a different temperature, this resistivity numbers now may change. So factor that affects resistance again is partly due to temperature. Now I think in our book, in the textbook that we use, we identified 3 factors already that affects conductivity or resistance. And among them, cross-sectional area, length, and then there's resistivity in that list. But here we omit the importance or the effect of resistivity as a factor, but instead added temperature. So let's not forget temperature when it is higher or warmer. Your metal when it is warm will have a higher resistivity value or resistance value. So factors that affect our resistance. Now, when we formulated some equations last time, we come up with an equation on electrical energy. And this electrical energy equation that we have last time, we wrote it, we write it as a value, E. And we relate that to work. So we understand that work is power times time. And therefore, if we multiply watts, which is the unit of power, and time, we will eventually end up with a unit joule. So watt second as a unit of energy is equals to 1 joule of energy. Now, therefore, if power in that equation E, so we come up with an equation E, and we kind of write that as VIT, and T represents time. So time is for letter T variable, and then therefore this one V sub I, V times I mean, should eventually by analogy would be the value of power. So if letter T variable here is due time, then therefore VI must be an expression for power. So therefore here we have now an expression of electrical power to be I times delta V. So delta V is an idea about potential difference or voltage. So it is similar to our letter V, this V that I wrote below. So V times I again is electrical power, and units of electrical power may be written in watts. So 1 watt of electrical power in terms of that equation could be 1 volt ampere, because it is in terms of the voltage and the current. So you could have a volt ampere to be your value of 1 watt as well. Now other units aside from watts is HP. And if we use HP, then 1 HP or 1 horsepower is 746 watts as well. Now there are machines or devices that do not use watts as a unit of power, but HP. So like aircon, like motors, water pumps. So it's equally important to mention the unit HP. Now we derive here power to be VI or I delta V. And if we go and use our expression, so we have an expression that is called as our Ohm's law. And from our Ohm's law expression, we have V to be equals to IR. This is our Ohm's law. And using this principle, that we can have a value for V here. Now, from our power expression, if we will change our expression V again, which is equal to I times R, and bring this IR, substitute it now to this value of V over this side. No? So you'll notice that that will become sorry, that will become I times IR, no? Which will now change itself, or once you simplify it, no? Becomes I square R. No? So I and I multiplies together, giving you I square. No? And then the attached resistance will now be joined here. No? Or this other equation on this end, no, will be, no, probably, no, you can get that if instead of substituting IR, you get the value of current, which is V divided by R. No? Now, if instead of IR, no, being replaced to the voltage, if we will replace instead, no, the value of the current, no, so from the current, no, so instead of this one, instead of replacing, no, sorry, instead of replacing the okay, just a moment. So instead of simply now replacing our voltage there, now what if we change instead the value of I? No? So if we replace that with V over R, and then there's another V value here, no? So you'll notice that V times V becomes V square. So you could have V square divided by R, no, as another equation for power. So power can be written in three different ways, no? Either VI, I square R, or V square over R. They will all end up with the same answer. No? They will all end up with the same answer. So uh this is our power, no, that is being, no, that is in our given, no, resistor. No? Now if you remember, we kind of added, no, another device called a resistor, and they look like this. So this resistor is different, no, from the resistance in the wiring, in a sense that this is an actual device. No? We denote it with this zigzag symbol, and we give it now a symbol R, no, still, because it has resistance unit. No? So we either call it as the fixed resistor or simply the word resistor. No? So when we have a resistor in our circuit, so again, so our resistor or fixed resistor, no, once it is in our circuit, then it provides an additional resistance to the whole circuit. No? But we could have now, no, a number of this new device, no, that we can add in our circuit. No? So in our succeeding diagrams later, no, we will see this new, no, device like your capacitor, no, similar to your capacitor, no, being added to our circuit. Now, from our electrical energy expression, which is power times time, no, we can also now write that value of power in terms of a kilowatt value. No? So from our expression of energy, no, so our energy again, or work, no? So we have a unit here, joule, as our unit of energy. No? So going back to our physics one, we wrote their joules. And again, no, if power is watts and time there is in seconds, no? So that's power times time. So watt second is a unit of joule. No? So this can be an expression of energy. No? Now, however, we can see that if it is a watt value, we can always convert it into a kilowatt, another way of expressing watts. No? And our time in seconds can be expressed as hours. And therefore, no, watt seconds can take, no, a whole new unit, no, which is kilowatt hour. No? Kilowatt is simply watts, no, in terms of thousands, and seconds, no, can be changed into a unit hour, no? And we could eventually have a kilowatt hour just like this one, no? And then this kilowatt hour value, no, can be equated to a joule, no? Now we will see that at 1 kilowatt hour, no, energy, it is 3.6 million joules. So look at the expression, 10 to the 6. That this one is telling you, no, that a joule, no, is relatively a small quantity. It is a unit of energy, but that unit is a small quantity. Therefore, no, we don't use that, no, to express, no, the energy consumption in our homes, no. Most of our or no, all of our energy consumptions is commonly expressed in kilowatt hour, no? But this kilowatt hour and joules, no, they can be converted one with the other, no? But however, in our homes, no, we don't use joule because maybe at the end of the month, if the unit that we are using there is joule, we could have an energy consumption in our house that will reach in millions of joules, no, every month. Okay, so that's why, no, to avoid maybe, no, a shocking value, no, that you will be given by more power, no. More power is a utility company, no, that provides us with electrical energy. That more power will send you, no, that this month you have an 800 million joules of energy used, no. So I think, no, that is not really, no, that does not really sound good, no. So to make it more practical, no, we use a bigger quantity of energy called kilowatt hour, no? Okay, so maybe you could just have there something like 150 kilowatt hour of consumption. Uh, and again, it is quite more appealing, no? Appealing to the user or consumer, no? Okay, so we have, no, another way of expressing our, no, electrical energy, no? And I think, no, the cost of 1 kilowatt hour would be something like 9 pesos or 10 pesos, no, for every kilowatt hour of consumption, no? We don't equate, no, the joule value in terms of energy cost, no. So there's no value there, no, that 3.6 million joules is 11 pesos, no. Usually we write it in terms of kilowatt hour, no, ang cost, no. So number of pesos per kilowatt hour, no. So that's your energy, no, unit, no, cost of electrical energy, no. Okay, now moving forward, no. So again, we introduced the concept there of our resistor, no? And maybe, no, in our next slide we will encounter, no, one. So here is again, no, a picture of a resistor now in a circuit form, no? Now we will see that some of these resistors or appliances, no? So maybe our resistor, ladies and gentlemen, could be similar to a bulb, no? So a bulb, no, is probably an electrical appliance, but it only consumes a small amount of energy, no? Now, other words for this electrical appliance could be a load, no? It's the load or the equipment that you put in your outlet, and maybe you can connect them in two different ways, no? So one way to connect them is connect them, no, in series, or maybe connect them in parallel, no? Now here's a picture of a series connections, no, of bulbs or loads or appliances. So each of these bulbs could be equivalent to a resistor, no? There is a fixed value of resistance in each of these bulbs. That's why, we can have them, with a symbol R1 or R2, no? So we could have a series connection or a parallel connection, just like this, no? Now, there are principles that governs how they are combined, no? The resistances. So one is for series connection, and then another is for parallel connection, no? The same way for our capacitance in our topic in chapter 3, no? We have also a way of combining capacitances there when we connect them either in series or in parallel, no? So the same is true for our resistance. Now we can call the total resistance, no, as termed as equivalent resistance. So REQ, guys, this one, no? So you notice there's only one, no? So why is it that there's only one, sir, when we are looking at two, no? There are two resistances here, pero nga isa lang daang ginsulat, no? Because again, no, they get the total already, no? So they sum up these values together, no? And again, no, there's a rule that they do, no, to be able to combine the resistances, no? So these two resistances, when you make them into a single, no, equivalent resistance, then you must know how to add them up, no? So for parallel connection, this is how they do it, no? So this one is for parallel connection, no? So this is parallel connection. Now for series connection, then this is how we also get, no, the total, no? So this is how we get the total resistance. So that's for series, no? Okay, so again, no, one single resistance here, no, is able to we are able to have it, no, because we know how to combine, no, the resistances together, no? So for series, what you do is to simply, no, add the resistances, no, R1 plus R2. But for parallel connection, then you will employ the reciprocal idea, no? So 1 all over the total resistance, or REQ, is equals to the sum of the reciprocals of the individual resistances, no? 1 over R1 plus 1 over R2, no? And if you recall, no, finally, no, if you will get the total resistance here, then you will get, no, the final reciprocal value, no, to be able to get REQ, no? So, but maybe now in a future example, then we can see how it is applied, no? Now going further, no, so let's just use the next diagram, no, to illustrate the concepts that divides, no, our series connection from our parallel connection. So this slides, no, sums up how we combine, no, our resistances, whether they are in series or in parallel, no? Now some of these principles, no, let's just have, no, a so maybe, no, there are questions here that you would like to read also, no? I will not go into this slide anymore, no? But maybe, no, as to the question why a bird, no, is safe when it is landing on a kind of a wire, no? So if a post has a wiring there, no, that is bare, and it is having, no, a very high voltage, why is it that the bird does not die, no, when it is sitting exactly on a wire, no, that does not have any insulator, no? So maybe, no, you can read this one, no, and try and understand, no, what is with that condition there, no? So those are things, no, that probably runs our mind, no, runs in our mind, no? A bird, no, that is does not have any gloves there, no, that it does not wear any protection at all in its feet, but it is able to land, no, on a wire that is having, no, several thousands of volts, no? So why, no? So perhaps, no, that's a question that maybe, no, it's worth answering also, no? But let's just move on into answering instead, no, Ohm's law. And again, no, for our Ohm's law principle, we have an equation that we write, no, either as V equals IR, or we can write it as R, no, and divide V by I, or we can have I, no, current I, and divide, no, V over R to get the value. So Ohm's law can be written in three different ways, no? Not only V equals IR, no, but you can transform it, no? Now let's read the question. So all devices are required to have, no, identifying plates that specify their electrical resistances. The plate on a certain steam iron, no, states that the iron, or the steam iron no, carries a current of 5 amperes. And when connected no, to a 220 volt source. So question, what is the resistance in the steam iron? No? So perhaps no, a steam iron is heating up, and therefore no, this is a device that must have no, a high resistance no, for it to heat up. Now, among the values that are stated, I is provided. No? First value that is given, we have a 5 ampere no, current that goes around our circuit. And next is that there is a voltage of 220 volts. No? Now, again, in our circuit, we can draw maybe a simple one, like this is our circuit. No? So maybe you have a battery here. No? There must be a source there. No? So the source is your battery. And then on the other side, no, you have your resistance over here. No? Okay, so when you turn on your circuit, no, so this is your R. And the question is, we don't know how much is the value of R there. No? But no, when the circuit is turned on, no, so you have here a voltage V, which is 220. And from here, we see that there's going to be a current that will flow in our circuit here. No? So current will travel from the positive side, no? And will now go into your resistor. No? So we label the current, by the way, as I. And the current there is 5 amperes. No? So there's a current that goes around our circuit. So if we will try to use our Ohm's law, then our Ohm's law will now give us this equation V over I. Okay. When we substitute 220 by 5 amperes, then we will get a resistance now of 44 ohms. No? And again, remember, ohms is written now with the symbol omega. Okay. So we have an omega symbol added here. No? Now, let's have this equation. So now the answer for the first question is 44 ohms. No? Now, going into the next example, so we have here, no, maybe still, no, we can think of it something like this, but with a different given. No? This time around, what is given is R. No? So R is provided, voltage is provided. No? So we have a 50 volt source, and it is connected to an 8 ohm, no? 8 ohm resistance. And therefore, no, if we will try to calculate I, then we will be dividing V over R. No? So V over R, still Ohm's law, now gives you 50 volts over 8 ohms. And you'll end up with a current of 6.25 amperes. No? Now that 6.25 amperes, if that's the current that we are looking for, that will also allow us to find the power, no, that the circuit needs or the heater needs. No? And remember, we have 3 equations for power. So if we will calculate the electrical power, first formula, we can use VI. No? So that's possible. Now, actually, VI is an equation that we can use here. No? But what they use as an equation is instead the I square R equation, because it is referring to the device, no, the heater. But even if we will use V times I, for this one, no, since there's only one device attached anyway, we can still end up with the same answer. No? But VI, no, may be not really safe, no, if you have a lot, no, of other resistors or appliances connected. No? Now, the power rating of the heater here, no, will then be, no, the current you square it, no? And then multiply it with the resistance of the heater of 8 ohms. So 6.25 square times 8, no, ohm will give you 313 watts of power. No? So this is how much power, no, is being used by this heater. Now, if you multiply that, no, in terms of the number of hours of use, change watts here to kilowatt, then you will know, no, that in 3 hours time, no, that's how much kilowatt hour is being used by your circuit. No? So your heater will need that much of energy, no, in every hour that you are using it. No? Okay, so we have here power and we have current value. No? Okay, let's pose for some questions. No? Now, going into the last, no, slide for this morning. So we are completing our discussion on chapter 4. Now, this topic here, this last slide that we are showing, no, is actually an application of chapter 5 discussion, which is about the resistances that are connected in series or maybe, no, in parallel. So this is not our topic for today. No? So let's just go into the next chapter that will now deal with this example. No? So we have chapter 5, guys. And chapter 5 now is the one that I posted in our discussion board in Canvas. No? So if you have time, no, kindly react to the discussion question there. No? So it simply asks a matter on on DC, no, direct current. No? So maybe you can read more on the direct current. Now, one thing about direct currents, this is the one that we see in our battery. No, there it has a fixed positive and a negative, no, terminal. So, however, no, when we have, no, when we use your what's that, no, so when you have a an appliance in your house that you will plug in an outlet, no? So maybe here is a picture of a socket, no, or no, we plug it in a socket, no. So we are not really concerned, no, whether we plug it upside down, no, or in any other manner, because there's no positive or negative end to this plug. No, there's no positive or negative. No, but but that is not true whenever we are dealing with a battery. No, so when we connect our battery in a remote control, we are conscious, no, that we connect it properly, that the positive side of the battery is connected to the right direction, no, in your remote control, no, or in any electronic device, no, that needs battery. But no, again, a plug like this, no, you don't need to really worry because it can go into reverse manner. No? Now, the one that is the counterpart of direct currents are what we call, no, alternating current. And the one that we use for, no, the alternating current are the equipments or appliances in our house. No, so the source of the power of the electrical appliances in our house uses AC. Okay, so you don't have there a battery where you plug your electric fan, no, or your TV in your house. No, so there's an outlet there that runs in alternating current. So the alternating current, again, no, compared to a direct current, no, it has no positive or negative terminal. No, so you can simply swap, no, the plug, no, the male plug that you have in your house. No, now in direct currents, no, again, there is a specific flow where the current is moving, no, and that is from positive to the negative end. So that's why, it's important that you connect the battery properly. No? Now, so that's about our DC. No? Now, here's the image again, no, about that series and parallel connection and some of the ways, no, that we can find the total resistance or the total equivalent no resistance, REQ, or sometimes they write it as R sub T, no, RT for total resistance. Huh? Now again, we can have not two different sets of circuits, one for series and maybe now one for parallel connection. Huh? Now for our series circuit, now let me just change the notations that we have here. Now, okay, so we kind of rearrange no and change no the representations of our R1, R2, and R3 now with these given values. Now, once the circuit is eventually turned on, now we know that it will have current no, that will flow from this side. So it starts from the positive and it will go to the rest of the circuit. No? So one kind of current will pass through resistance 1 and we will call it as our current I1. No? I sub 1 again is the current that passes through resistance 1. No? Now another current will eventually pass through resistance 2. No? So here now it will have another I sub 2. No? And finally, maybe here below, you'll have your current, no? I3. No? So the current there will be going around no? Our series circuit. No? Now, what we will also observe is that this current that goes around our circuit, no? Which starts first no? From our battery. So the current that comes out of our battery, we can call it as I sub T. No? And again, IT, you can call it as the total current. Okay. Now you have your I1. You have your I sub 2. No? You have your I sub 3. And again, these are the currents that passes in each resistance. No? So each resistance has its own value of current. No? And eventually, that current goes back to the battery. No? Now, from our Ohm's Law Principle, no? So based on our Ohm's Law Principle, whenever there's a current that goes in our resistance, so I1 passing R1, then it will develop no, into a voltage. So the product of I1 times R1 no, is eventually no, creating a voltage. So there will be a voltage for R1. Likewise, no, I2 times R2 results in another voltage. Okay, so that is of course equivalent to I2 R2. And V3 no, there would be I3 R3 value. No? So again, these voltages results whenever we let current pass through this device. Now, how do we know that there's really a voltage there? No? Now, maybe if we get a measuring device called a voltmeter. So we saw one voltmeter in our simulator. And if we will put that in our circuit here, so maybe we can test if it's really true that there's a voltage here, so we can connect another device somewhere here. So let's just use a black color probably. So supposing we get a wire, we connect it to our resistance 2. And in our resistance 2, we will get a voltmeter. So we will have here a voltmeter. We connect a voltmeter here. And that voltmeter again, if you are going to represent that in some kind of a symbol, maybe it will have a circular thing here. And there's now a wire now that you connect across your resistance. So you can connect actually 3 voltmeters in each of the resistor just to check if there's really a voltage. So again, now with this voltmeter, you will be able to get V1, V2, and V3. And we will discover that V1, V2, and V3 has a relationship to our total voltage. Just like our I1, I2, and I3, the currents that goes around, it has its own relationship to our total current. Now, if the circuit is connected in series, now the first principle that we will get is that the total current I sub t happens to be the same as I1. It is equals to I sub 2. It is equals to I sub 3. So this is the first principle of series connected resistances. All the currents simply gets in, gets out, gets in, gets out to the different resistances, and eventually returns back to the battery unchanged. So the current there simply goes around. However, it is not being reduced, or it is not being increased as well, but it is simply entering and getting out of the resistances and returns back to the battery. So now that's the first principle governing series connection. Now, when we relate the voltages that results whenever we have current and resistance, the values of our total voltage, so V sub t, we call this as our total voltage. It is related to V1, V2, and V3 by adding them. So if you add up all the voltages together, they are equal to the total voltage V sub t. So we have here a V sub t value, which we call as the total supply voltage. So that is the one that is provided by our battery. Okay, so V sub t. Now again, its relation to our individual voltages is that they are added up together. Now, what then is the relationship of our resistances? So the third principle is that if you want to find the single equivalent resistance, so supposing we are to combine all this, we add up R1, R2, and R3. So our circuit will simplify itself, and you'll probably simply have this one, that there's only now one single value of resistance that we end up with. So we call this single resistance here as R sub t. Okay, so your R sub t now is your combined resistance of all three resistances. So we can actually group them together into a single equivalent resistance. And on this end again, maybe you have there your battery. So this is your battery. So this is another way to write the 8-volt battery. Another way is if you see that in the diagram above, it's circle with a plus and minus sign inside. But this could be your, again, your V sub t. Now, your V sub t, you can always relate that in terms of Ohm's law to your total current that goes around in your circuit. So somewhere here, maybe there's a current that is going around our circuit. Again, Ohm's law will tell you that that's IT, RT is equals to total voltage. Now, with that idea, our total resistance, so R sub T total resistance is simply R1 plus R2 plus R3. Now, if there are more resistances connected in series, then you just add it to the equation here. So these are the three governing principles in series connection. Okay, so can I see a thumbs up if you understand the discussion here, or if you have a question? Do you have any question about the principles that we just come up with? Okay, it seems that there's no question, so let's just move on to the next diagram. So We will now go into parallel connection. So let me just remove some of these things now that I wrote here. So maybe now that's how we represent our circuit there. So these are the three principles again, the one that we wrote above. Now, going into the parallel connection. So here's our parallel circuit. Now let me just modify the things that we find here in our circuit. So we change again now the values of our resistances, R1, R2, and R3, just to have a mindset that we have unorganized values of resistances. The slide there now gives us different sets of numbers. Now the battery again is equal to 12 volts, and we understand that when we connect the circuit here, then we would naturally have a current that will eventually flow from the positive side of the battery going into the three resistances. Now, as the current passes here, it will split itself. It will move in three different directions. So this will be your current 1, current number 2, I2, and this will be your current number 3. Now, the three currents in this case is a result of splitting up. So the current moves in three different directions. So meaning I1, this is your I sub 2, and this is your I sub 3. Now, again, if you think of it, current separates or splits in three different directions. So maybe with that idea, it will give us the first principle of parallel connection, which is that the total current that is provided by our circuit will split up into I1, into I sub 2. But when you add them actually together, they will simply combine themselves, and it will be equivalent to the current provided by the battery. So the battery current, which we call as I sub t, simply goes in three different directions. So naturally, the resistance with the least value, like this 8 ohms, this one will take the bigger amount of I total. So as it splits, more current will pass 8 ohms, and another one will pass a little more of that, will pass on the 10 ohms, and the least value will pass on the 24 ohm resistance. And what's the reason? Again, the device or the portion of the circuit which has the greatest resistance will most likely be affected with the smaller amount of current.
Sir, excuse sir, nakamute yata, sir.
Yes, no, sorry, no. So again, no, we have again, no, this principle, no, that current in our circuit, no, is equal to one another, no, but no, the voltages, oh no, the voltages are equals to one another, but the currents, no, when you add them up, they are no equal to the total current. No? Now again, no, the idea again of the voltages to be equal is that any appliances that are attached in our home, they must have 220 volts each. They will not work now if they have a higher voltage than 220, or they will get damaged when they have a voltage that is lower than 220, like 110. So again, the idea of parallel connection is that the voltages should be the same all throughout. Okay, so these two principles will now allow us to have the total resistance. So what if now we combine our circuit and we add all these three resistances together? How do we add them? Now again, if we will look at the first principle of current, and we notice that the currents are added together. Now the current that passes in I1, so if we think of I sub 1, now for I sub 1, you'll notice that we will divide the value, so current 1, we will divide there the voltage V1 with the resistance. So notice Ohm's law tells you to get current 1, and you can divide V1 and R1 together to get the current 1. Now the same is true when you have to get the total current. So if we base that on Ohm's law, so IT, so I total, sorry, so IT is equal to VT divide by RT. And what is VT RT? RT must be the total resistance. VT is the total voltage. So therefore, to get this current that comes out of the battery, then we can divide these two. Okay. Now again, with that analogy already, then therefore we know that I sub 2 will follow. That will just simply follow. So that will be V2 R2 and I3 will be V3 divided by R3. Now again, the slash there is a division operation. Now, going back to this equation number 1 principle. So let's go back to this first principle here that I checked. Now, if we now formulate our next sets of equations, if IT now being VT over RT, so let's write it in terms of voltage and resistance. So that's the value of IT. Now, if IT is equal to I1, then how do we write I1? I1 will be written as V1 all over R1. Okay, are you following me? Then our I2 is V2 all over R2. And finally, our last value of current there, I3. So I3 must be V3 all over R3. Okay, now again, we divide them. So we simply now replace that with our resulting expression in Ohm's law. Now, from our second principle, we notice that these voltages, they are simply equal to one another. So V1 is simply the same as V2, simply the same as V3. So why not call them instead as V sub T? So if we call them V sub T, they are simply equal to each other. And in algebra, in your math, when variables are the same, you can actually factor it out. No? So if they're all equal, no? So question, what common variable, no, can we get or extract out of them? No? So of course, no, if VT, no, is representing V1, V2, and V3, then we can, no, simply, no, get it out. No? So VT, no, if we get it out, since it's common, so what remains in this side is 1 all over R total. No? So that's what results, no, when you remove the numerator and move it out. No? What remains in the expression, since it's a denominator ng RT, what remains in the numerator would be 1. No? Now again, if V1 is VT, no, then we can also get it out, no, from our expression. No? V1 again being equals to VT, V2 being equals to V sub T, V3 being equals to V total. No? Then what will remain inside the parentheses? Again, the numerators will all become 1. No? So 1 over R1. Then the next expression, no, ang V2 over R2, since we move out V2 already outside and call it VT, then what remains in the numerator will be 1 over R2. No? Okay, then next is V3, no, nagwa man ang iyang numerator, then what remains is your value of 1 as well. No? So ano no, ang aton values karon nagwa na factor out na to. No? We were able to factor out the value. Now, you'll notice that after factoring it out, no, V sub T is found on both sides of our expression. No? And if you divide them by V sub T, then they will eliminate or cancel out. Now, when they cancel out, what remains is a reciprocal expression that, no, ang aton numerator will now all become, no, 1. No? Okay, so this left side, no, will now be equivalent to 1 over R1. Then now added to 1 over R2. No? Then next, you have to add, no, the last value there, 1 over R3. No? So, ano aton nga final values karon, no? Okay, so now since we are dividing it, no, then we now have this relationship. So we can get the total resistance actually by getting the sum of the reciprocals of each of our resistances. No? So this is quite challenging, no, compared to our series connection. When in our series connection, we simply add the individual resistances. So we can have a single value when we combine all these three resistances, no, and call it into an R sub T value. No? So again, now we can come up with one single answer, no, whenever we are dealing with parallel connection. No? So okay, now so we have again now 3 governing principles. So these ones in the boxes are the governing principles for our parallel connection. So may I pause for a while if you have a question? Huh? So I will entertain some questions. Now I noticed that we have barely a few more minutes left, and it seems that there are no questions. So before the time now, there are around 6 minutes more. So I think we will end our lecture if there are no questions with you. No? Now in your Canvas, no, in the module in the Canvas, the next succeeding slides will be a combination of series and parallel connections. But again, the 3 principles that we pointed out for series and parallel connection is summarized for you. No? So therefore, when you have a combination circuit, then you can simply apply which principle is applicable to that particular portion of your circuit. No? But anyway, now you can try this out. No? So the previous example and the previous slide, you can apply there the series connection and the parallel connection also, no, to find total resistance, total current, total voltage, and maybe the individual voltages and currents in each of the resistors. No? So I think now that's all for this morning, no? Unless again, no, you have a question, no? But good morning to one and all, except for those that I will check, no, their names, no, to those who just get in our Zoom, no.